Good afternoon. It's really wonderful to welcome you here today. And I thought I'd just give you a little background both on the reason for the lecture and on our speaker. For those of you who have not been following some discussions within the university and the board, I wanted to just alert you to the real sponsors for this event, and that's the Advisory Committee on Social Responsible Investing, which is a committee composed of trustees, faculty, and students, and was constituted by the Board of Trustees to be knowledgeable about relevant socially responsible investing issues and to advise the board on policy issues. The committee is currently considering a petition submitted by a group of faculty and students calling on the university to divest from investments in fossil fuel producers. As part of these deliberations, the committee proposed, and I strongly supported, the idea of holding a series of BU community forums in which recognized experts would give us their insights on subjects relating to climate change and the role of fossil fuels. The intent is to provide information that both educates the committee as it deliberates, as well as informs the broader Boston University community. This afternoon's event is the very first of this series, and I'm very pleased that John Reilly agreed to be the lead-off batter in the series. And lead-off batter is a metaphor for next week, I guess. But it looks like we will play baseball without snow, but it's not clear. John is a senior lecturer at MIT's Sloan School and co-director of MIT's longstanding joint program on the science and policy of global change. John is an expert on the role of human activities as a contributor to global environmental change and the effects of that change on society and our economy. His research focuses on the integration of economic models that describe human activity and models of biophysical systems. He holds a BS degree in economics and in political science from the University of Wisconsin, plus an MS and PhD in economics from the University of Pennsylvania. I'm grateful and pleased that on rather short notice, John agreed to come make time in his busy schedule to come and give a talk entitled The Economic and Societal Impact of Climate Change. John, podium's yours.
Thanks, Bob. Well, thank you very much. Well, it's my pleasure to be here, actually. The program I co-direct with Ron Prinn, an atmospheric chemist at MIT, was founded with the idea of contributing to the public debate on this. And so here's one of the important public debates. So I'm happy to come here. That's why that's the argument we make for research sponsors of the program. With that said, the very first thing I wanted to do was, obviously in this area, I think it's important to be completely transparent about where things come from. And so these are funders of the program that I run. So you'll see there are a number of large energy companies in the program, but also other companies. And we get funding from most of the federal agencies that are involved in this. So the industrial funding is mostly as a gift fund. So there isn't a specific specific research goal of it. But that's the background of where funding for our program comes from. I wanted then to step back a bit and make a few remarks about climate change in a broader global change context. So our program is a program of science and policy of global change. The climate issue is, of course, an important one, but it's wrapped together with many, many other issues. It's wrapped together with air pollution generally, with food, with water, the energy issues. So many, so we don't think you can look at one of these problems in isolation. You need to look at them together. So, I say here many in the world are poor, but most countries are advancing and some rapidly. Well, we've hoped that the world's poor could advance and become wealthier, and now we're seeing that happen. But the population and economic growth we are seeing creates further demands on natural resources and use of energy, and probably, unless we do something decidedly different and send some different signals to the planet, probably fossil fuels. And I'm going to go through some forecasts we do that suggest where we think the world is heading given the current policies we have. So if this happens, of course, we see climate change bringing rising temperatures, changes in precipitation, river runoff, soil moisture, sea level rise, changes in tropical storms, air pollution, wildfire, and the list can go on, with consequences then for human health, agriculture, infrastructure, and ecosystems. So that's the kind of the challenge there. We're finally getting some ground on getting the poor countries to rise out of poverty and become wealthier, but that has its own consequences. Still, then we have in the world, the current population, some 800 million people lack clean water, 2.4 billion are without sanitation, 1.3 billion with no electricity. Food production in the world, estimated by FAO, needs to rise by 70% by 2050. Irrigation is the biggest water user, and while it's only 70% of the land, it accounts for 40% of cereal output. So already with this list of things, you can see some trade-offs and possible synergies in the impacts of climate change, mitigation, and development goals. This need for more electricity, for people to have access to energy, is a challenge because that may mean more fossil fuels. The water problems, if we have climate change and that changes water availability, that could exacerbate or alleviate in some cases, I'll suggest, as we go forward. Our approach, it is MIT, so there's no model that's too big for us to try to imagine we can create. We use this MIT Global Integrated Systems Model, Integrated Global Systems Model, that has a whole model of the world economy and a whole model of the world's oceans, atmosphere, urban areas, land, ocean, et cetera. And we have shown here some of the connections we see among those sorts of things. We, of course, see a whole list of pollutants, both greenhouse gases and others, floating into the atmosphere. Those changes have some effect on CO2, methane, N2O in terms of we're trying to control emissions. There's natural sources that come back. But then, water resources, agriculture, energy demand, sea level rise, human health, all being affected by what we do to the atmosphere. So I just wanted to put that up. I'm going to show some figures from some of the work we've done that relies on this system, but that's the machine in the background. One of the things we've started to do every year is to release something we call the Climate and Energy Outlook. So since we have this integrated model, we've tried to put it together and kind of then can give a forecast of where the world is going pretty comprehensively, looking at everything from energy use to economic growth to land use to emissions to climate to ocean acidification and sea level rise. So that's it. So we start with kind of an economic growth scenario here, and this is one growth scenario. What you see is the dark blue on the bottom, what we have long considered the developed world: the United States, Europe, Japan, Australia, New Zealand, Canada. The mid-blue wedge in the middle is the other G20 countries. So I don't know if you follow economics, but there was the Group of Eight, which is the major developed countries that had long planned the world economy or worried about it. With the expansion of places like China, India, Russia, South Africa, Brazil, Korea, that group has expanded to the G20, realizing that those countries need to participate in this, thinking about the global economy as well. So that is a rapidly growing group, and as you see, growing substantially, and taking up a bigger wedge of that economic, or getting a bigger wedge of the economic pie. The top is the rest of the world. In our modeling apparatus, we actually have this resolved in greater detail, but it's kind of interesting to look at these three groups because there is a different story. I mean, the developed countries chugging along, other G20 growing rapidly, rest of the world growing fairly rapidly. But one of the features of economic growth is that when you start out at these lower levels, even if you're growing faster, it takes a long, long time to catch up. So people are actually talking of when are developing countries going to be rich as developed countries. Well, not in this, not in this century, even if you have them growing relatively rapidly. I mean, a few countries could do that, but it takes a long time to catch up, and the growth rate has to be very much faster. I would say that, that we have a population figure and the population figure is really quite dramatically different. It illustrates, one of the other issues. Developed countries' populations flat and falling. The other G20 rising a bit but stabilizing very quickly, and the rest of the world exploding. So you have a whole bunch of population in that region that's growing, but that's the other aspect of that problem. So what does this look like in terms of energy use for the world with current energy policies? Well, here again, I've broken this down into these three regions. The developed countries on the left, you see energy use is flat or slightly declining. We've assumed that the developed countries here will take on their Copenhagen pledges of reducing greenhouse gas emissions through 2020. We haven't put any additional policies on beyond that, but that stabilizes energy use, and you see there's still coal use on the bottom, but it's going away. The rest of the world is chugging away, growing, but what you see is this other G20. So that's the China, India's, Korea's, et cetera. And that is, I like to say, is becoming an energy world of its own by 2050. So by 2050, its 500 exajoules of energy use are about what the total world uses today. So we see that happening, even though we have factored in some of the policies China has proposed to do, but it's still growing rapidly. And that's because these countries, the incomes are growing rapidly, and there's still a lot of people whose energy needs have not been served. So it's really the big challenge we have. We're trying to reduce emissions, but we have big parts of the world that, if they're going to be wealthier and they need to kind of get these energy services, are going to need a lot more energy. And in this world we have here, even with fossil fuel prices climbing a bit because of depletion, a mostly fossil world, because the alternative technologies, the renewables, the biofuels, the nuclears don't take off that much without further incentives for them or disincentives for fossil fuels. And one of the challenges here for the alternative energy sources technologies is that we're always imagining their cost is falling a bit, but as we've observed in recent years, guess what? Technology isn't stopping on the fossil fuels. So we have this whole shale oil and fracking sort of technology, which has also all of a sudden opened up all kinds of new resources. When I started doing this work back in the early 1980s, we looked at unconventional oil sources and saw tar sands as this strange thing that might one day be used. Now it's, of course, a massive development already. So people have looked at just conventional oil, conventional gas, reserves and said, oh, we're going to run out of it, and won't that be, well, some people think that'll be awful, others say, wouldn't that be wonderful? That'll force us to solve the climate problem. Unfortunately, there's enormous amounts of this stuff, and the technologies to get it out keep getting better. So what does that mean for the planet? Well, it leads to significant environmental change. We have the historical data plotted up through to present in the dark black line, and then then we're seeing in the top left panel temperature rising between about 3 degrees or 3.2 up to nearly 6 degrees C for the globe. We'll see increasing precipitation and global sea level rise, although this is a sea level rise of half a meter at the highest, but this is just the sea level rise due to thermal expansion. So we actually expect there to be more from ice melting as well. And then, this has gotten some press recently, but, it kind of is one of the silent sort of stories, is that with all that carbon dioxide in the atmosphere, the reason it doesn't go up faster in the atmosphere is the ocean is taking it up, but that causes ocean acidification. So this would have ocean acidification proceeding quite a lot. So that's a broad climate, a broad picture of the global climate. what does that mean for some of the things that are closer to what we rely on as human beings? Well, one thing to be concerned about is water stress. And so these 4 panels are from these projections, and the top left panel is showing water stress currently. And you see that there are already large areas of western United States, northern Africa, and into Asia that have a fairly significant water stress problem. The right panel is 2100. It's a little bit hard to see what's happening to that, the differences, but the bottom panel, left panel, is the change in water stress. And so you see those orange-red areas are things where water stress is increasing. The green ones are actually where it's reducing. Now, as we showed in that previous slide, global climate change will cause precipitation globally to increase, but not the same everywhere. So, so this is actually the change in water stress. Some of the areas are actually improving. Now, we are factoring into this the idea that with economic and population growth, there will be more demand for water. So the developing countries in particular, oftentimes we see that growth in demand for water as the bigger cause of water stress than the change in climate itself. So this idea of how these problems interact in a broader global change story. I mentioned earlier that, and so this is pluses somewhere, minuses other places in terms of the climate implications. Another interesting case, this is a paper that is now a few years old, where we're looking at, I'm plotting here, food prices, a crop price index, livestock price, and forestry price index. And this is projecting them going out into the future with economic damages, with damages occurring due to climate, CO2, and ozone. Now, interestingly enough, the no policy case is the solid black line, and we're actually getting the least food price increase in that scenario. When we do the short dash line, that's an energy-only policy, and you see we don't get much addition. The food price is almost the same. Well, what's going on here? Well, you know, the raising energy cost, solving the climate problem means raising energy costs, and agriculture is actually a big user of energy. So it's avoiding some of the damage of climate change, but it's now energy is more costly, so those things just coincidentally about net out. What are those top lines where things look really bad? Well, we extended this carbon pricing idea to land use carbon. So the idea being that, you know, if you grow more forests, that will store carbon. So that ends up taking a lot of land away from agriculture and causes prices to rise even more. So, you know, we still may want to solve the climate problem. Agriculture isn't the only story, but there are these interesting trade-offs in the solutions we take as we go forward. You know, the challenge here, I mean, this term came up a few years ago, and I had to admit I was fairly negative about the whole idea. We had sustainable growth, but apparently people didn't like that term, so people created green growth, and it seemed a bit like a bumper sticker rather than a serious idea. But I've kind of been converted over the years, having to write a couple of papers on it. And so the green growth idea is one that says, you know, we want the economy to grow, but we don't want to have environmental damage. And so I guess my question, is there really any other option? I think over the past, you know, maybe the current generation has fixed their heads, but I think during my career, a lot of times we began seeing the environment as a luxury. It's a luxury good. It's something you can afford when you're wealthy, and so it really wasn't gonna, really it's saving some spotted owl somewhere or something. So it isn't really, it isn't really affecting the economy. So you had to give up the economy to save this environment, which was kind of murky for some people. Well, when we see the environmental problems affecting agricultural yields water availability, our human health, that has impacts on the economy. So that is actually undermining the economy. So my argument is that if we go ahead on this path, it's hard to have growth like I've described if it's not greener than what it is, because the very growth we're kind of undertaking will undermine the economy by causing these sorts of damages. So my argument is there really is there is not really an option to somehow solving this environmental problem, but that is a research challenge. My supposed trade-off between economic development and environment is mostly a false one if the environment is evaluated properly. Environmental, as I mentioned already, and this false idea that environment is a luxury good. And I think this has changed. This is a different way to think about the world because the scale of human activity is now at the size of Earth systems. You know, we used to just be able to kind of pollute some area and move on to someplace else, and it didn't really affect us. Now we are affecting Earth systems. We can't really escape it. So it is probably a change, a fundamental change in that now in the past we could escape it, now less able to. So what is the challenge here? Well, the challenge is really coordinated policies. I mean, as an economist, our solution is simple: internalize externalities into the regular economic decisions. So that's the carbon tax or the pollution tax or other sorts of things, so that the real cost, the real social cost of using these different things these different technology fuels are reflected in our market decisions. But we need better data on these non-market linkages. You know, if we tax the wrong things too much, then of course we can worsen the problem as well. So it really does require, you know, really careful evaluation of what's going on, and then valuation of existing links, this expanded national income and product accounting, you know, green accounting people call it, and then formal modeling of policy impacts, trading off cost of abating versus benefits of abatement linked to economic growth. And then, of course, the challenge here, ever more, is we can't do this as even a single country. It requires coordination among countries, as many of the environmental effects are transboundary. Climate change is obviously the global problem, but you know, even tropospheric ozone you know, is transmitted hemispherically. So China's emissions of ozone precursors show up affecting ozone levels in the U.S., and U.S. ozone precursors end up showing up in Europe. So we are in this global this area where it's hard to escape the problem or hard to isolate ourselves from the system. So I don't know. I hope this isn't too geeky, but you know, this is the nature of the economy as we look at it from a economic standpoint: an input-output structure up in the left, and final uses by households, government, and total output, and then our basic inputs: the labor, capital, resources. What we've done here, to kind of, in some of the work we've done, is to bring these what people often call non-market environmental impacts right into the economy. So you see it. This is how you see it has an effect. So this was some work we did on health effects of air pollution. And so when you have air pollution and you get sick or die early, well, you need some medical services. So that's drawing resources away from the rest of the economy that could have been used to make someone healthier or some other way, or could have been used to produce an iPod or whatever, but it's drawing resources away. Similarly, when you're ill and not going to work, that's taking money out of the economy. And we expand that, and we don't just value the kind of actual labor that's going into the economy. We're concerned about the non-work time, and I probably use non-work time, I should do these little air quotes, because, you know, what are people doing when they're not working? They're taking care of their children, they're doing other sorts of things which has a great value. It isn't entering into our dollars and cents measure of the economy, but it's just as important as anything else in the economy. So we do need that sort of perspective. So what's an example? This is some work we did on China, looking historically at air pollution in China, and there's two policies we're looking at, just comparing air pollution compared to if you had just background levels of air pollution, you got rid of all the industrial stuff, or China just met WHO health standards. So the WHO health standards is on the left side, against background levels on the right, so obviously the background levels of numbers are going to be bigger. But you're seeing that a couple of interesting elements here. So we can look at just the impact on consumption, which is the market economy. You see from 1975 to 2005, we saw that growing from 11.5 billion to 38. That was actually 17% of the economy in 1975. So really a huge impact on the economy. We can also measure that as the change in welfare, where we have this broader measure of valuing, non-work time. So you see the numbers are bigger. That last percentage is a little bit odd because it depends on how we value all of the time of people, so you get a lot more time in there. So even though it's a bigger number, it's a smaller percentage of this big thing, which is isn't is different. The other interesting kind of thing here, though, is that China has kind of grown itself into a point where it's better able to take on the problem, because the rapid economic growth has made this growing number a much smaller share of the economy. So that is the benefits of being wealthy, that all of a sudden the problem, even though it's growing, shrinks as the size of the economy, and you have more resources to really take care of it. But it is striking to see these quite large percentages, off of what could have been otherwise economic activity spent to do other things. So then this is an interesting story here. I didn't take, one of the things we looked at with China and CO2 emissions is the trade and CO2 emissions embodied in trade. So we think of China as the big enemy here, that they're producing a lot of CO2 emissions. Well, of course, we know that we import a lot from them and they export a lot. So something like 23% of their emissions are actually associated with exports. So in this exercise, we took China and said, what if instead of doing all that exports, it relied more on domestic consumption, and what would happen? Well, of course, since it's still spending that money somewhere, emissions drop, but not nearly 20% in China, but then we're still going to need those products from somewhere else, so we import them somewhere else. So while that reduces emissions globally a bit, it doesn't reduce them that much. You'll see we're getting 26, 255, 23 globally in the reference. It drops a couple of hundred, but not nearly as much as you might think, just looking at that 20% of China's emissions are from exports. So that's one of the complexities of the issue. I think we oftentimes are patting ourselves on the back, saying, look, our economy, or someone is, if it's not California, it's Europe, saying we're much better than you. A lot of this may be embodied, that we're importing the goods from other countries. Then this is some work, I think, where we've asked, if you controlled conventional air pollutants, what would be the impact on fossil fuel emissions? Because these conventional air pollutants are coming out of combustion of fossil energy, and so if you have to start controlling them, does that make you do really different things with the technology and coincidentally reduce CO2 emissions? When we look at the developing countries, their willingness to take on big carbon policy is probably more limited, but they are concerned about conventional air pollutants. So what we've framed this here as elasticity. So if you do a 1% reduction in ozone precursors and PM, what percentage reduction do you get in carbon dioxide? So, and then we formulated this elasticity for many different levels for 4 different levels of the reduction. So China, at that 75% reduction, in order for them to meet their air pollution goals, that's the sort of reduction they need. And they're getting a 1-for-1 reduction in carbon in this estimate. Even in the US, we're getting a fairly big reduction for carbon. So that's a place where there's some synergies in these problems. We take on one problem and we get some benefits in the other problem. So that's one of the reasons to kind of look at these problems in conjunction. Similarly, from a technological standpoint, is the technology going to solve more than one of these problems rather than just focusing on one at a time as we go forward? Then again, coming back to the water issue, this is some work we've done looking at changes in Southeast Asia in terms of water stress and unmet water demand. This is one of those stories that kind of talks about how this issue isn't as simple as you first think either. One is you'll see probability density functions there. So that is actually, we've done hundreds and hundreds of runs to kind of try and understand what the future is going to look like, because we know that any one run is going to be precisely wrong. And then we have 4 different PDFs. The dark line, the dark narrow PDF with the bar in the middle is the range of variability in water resources we get today. The red bar is if we just look at the impact of economic growth and no climate change. The blue bar, the blue dashed lines are if we just look at climate change and no growth, and then the green is the combination of those two, not just added together, but we do the things as a system because they aren't necessarily additive, approximately so, but not necessarily. So we've looked at, the top is China, the middle is India, the bottom is mainland Southeast Asia. You'll see that in Southeast Asia, the climate is actually getting wetter, so that's kind of offsetting the growth. In China, they're all working to make things worse. In India, the climate effect is at least median, to not have much of a change. But the striking thing we do see in all of these, when we get to that future, is a lot more uncertain future. So the challenge is we know something's going to happen, but we're not very good at predicting what it is. So we have to be prepared to see things far outside the bounds of what we're used to dealing with. But frankly, in some of these places, we don't know whether that's going to be wetter or drier. It could be either. So that is really a big challenge in terms of trying to come to grips with what climate change means, both just coming up with estimates of the economic impact, but also then what we really do about it. And I've been over the years talked about how adaptation could get us out of a lot of this problem. But when you don't know what you're adapting to, it makes the adaptation challenge a bit harder. So I wanted to then turn to a couple of things just closer to home, what's happening in the U.S. Based on some EPA. We're working with the Environmental Protection Agency. This is just looking at projected impacts on air pollution due to climate. This is just saying, we're saying, let's assume that emissions are the same that they are now, but it gets warmer and the air patterns change. So we see that alone is causing increases in air pollution, particularly over the eastern United States. So for both, particularly for fine particulate matter, that effect is over the eastern part of the United States. For ozone, it's actually reducing ozone levels in the northwest and worsening them in the south and east. That was a reference policy without any climate mitigation. When we do the climate mitigation on the bottom, we're able to avoid most of those changes. So there is hope. This is some work on the impact of extreme temperature on mortality, again showing this reference case and the mitigation case. In both cases, we're getting some increase, but fairly substantial increases in the reference case where we don't have mitigation. This similarly is looking at another issue, which this had kind of, I think, escaped people for quite a long time, but just the impact of climate on labor productivity. So we think we're fairly, and this is looking at, of course, people who work outdoors, farmers or construction workers, this high temperatures can really affect productivity by estimates. And so you'll see that in this reference case, we're getting quite a large impact on labor productivity, not surprisingly in the south and southwest, but also, interestingly, going up into that mid-plains regions where even though we think of that as a cold area, during the summer, it gets very hot. And so you see an estimate of 1.2 billion labor hours and 91 billion in wages lost due to the unmitigated case. You can avoid a lot of that with the mitigation case. And then this is coastal development. Again, this is, and here's again one of those interesting interconnections of problems. One on the left side showing the cost if you don't have adaptation, the green line showing if you adapt, it costs you much less. So the adaptation is a powerful force for avoiding some of these losses. On the right side, we're seeing the damages by region, and interestingly, we separated out just that due to sea level rise, and that due from the combined effects of sea level rise and tropical storm surge. So this, and we've done some other work with this, if you take subsidence into account in many regions, those three things multiply together rather than just add. So you get, if you just look at the sea level rise, it's like, so that's not so bad, we can handle that. Now you throw in increased tropical storms, pushing that storm water ever further in, and it gets much worse. If you happen to be in an area that's subsiding, still worse. And so it doesn't really add together, it's really more of a multiplicative issue. I mean, here's another issue that I think 20 or 30 years ago we weren't really thinking that much about, but we've seen some of these heat waves in Europe and in the United States a couple of years ago where power plants have had to shut down, thermoelectric power plants have had to shut down because of the water temperature was so high they would violate EPA rules by putting it in. They'd essentially, I guess, cook the fish that they're putting in. So this is an estimate by 2050 of days of lost generation. And unfortunately, this figure, the bottom part gets picked off, but that dark red is like 90 to 140 days of lost generation. Well, if you're losing that much generation, the power plant is almost worthless, right? Now, you can adapt to this. You can put in air cooling or do recycled cooling or other sorts of things, but it's just one of the things we have to be thinking about as a society as we go forward if we face these sorts of warming temperatures. The last thing I wanted to focus on was, again, this adaptation challenge. And this is some work, this was the work we did for CERA to develop from the EPA workshop to develop some projections to look at different policies and different uncertainties in climate sensitivity. These are actually, for the US, temperature on the left, precipitation on the right, and their ensemble means of 5 ensemble members, because when we simulate the climate model, what the initial conditions are can affect the thing. But the ensemble means tend to smooth out the problem a bit. It's still kind of noisy, but if we actually look at the real scenarios, this is what they are. So this is again that challenge of adaptation. If we're looking over here at precipitation and we're kind of looking out to 2040, here's the range that we're kind of used to from historical experience. If you just look without those lines, it almost looks like it's not going up at all. But you see, as we go out in the horizon, we're getting more and more of those extreme high precipitation events in the United States. So unfortunately, or we're here today, that's 2015 about, and we do all of our planning with this historical background looking, but we really should, we really should be doing it with this revised projection that really is going to look at what the future is going to look like over the horizon of our investments that we're taking today. We're always lagging, unfortunately, behind with some of the sorts of things. If we're just looking at historical data. But this is the big challenge for the climate modeling community. I think we've been spending a lot of time saying, trying to convince people that climate change is real, which has been wasted a lot. Well, I guess it's not it's useful work, I suppose, but at some level, the challenge now is to make projections that are realistic enough and that represent the uncertainty so that they're actually useful for the adaptation decisions that people are taking, which are going to, which have a horizon of 5, 10, 15, 30 years, and that's where you kind of have trouble seeing these climate model signals rise out of the noise, but that I think is the central challenge now that we realize this is happening, and even if we work pretty hard to stop it, we're still going to see quite a lot of it. So that's where I will end. Thank you.
For some questions right now. I ask that folks use the microphones because we are recording it and we'll need for you to use that. We're here to talk about the topic at hand, and let's please be mindful that we've got a limited amount of time. If we could quickly ask our questions or make our comments, that would be wonderful. So please proceed to the microphones if you have questions. And Steve, you'll have to turn that microphone on, please.
When you talk about adaptation, can you be more sort of specific about what are all the things you're thinking of when you talk about adaptation to climate change, and particularly the value added factors of this or that kind of adaptation? Yeah.
Well, of course, that is, it's the impacts of climate change spread across so many different things. It's a different problem in every case. There's a great guy, Paul Kershen, who's at UNH now. He was at Tufts for a long time. He spent a lot of time in East Boston, actually saying, with sea level rise and coastal storms, how are we going to protect East Boston? So do we kind of build some berms? How do we get it started? Do we try to do it everywhere? Given that we're uncertain about the future, can we have a strategy where we build a few now, then we put in some later? What parts of the thing are actually, what parts are most critical? What's subject to flooding? Can people raise their houses? So those are the sorts of questions that go on there. I spent a lot of time at the Department of Agriculture and think a lot about the agricultural sector. So there is plant and crop breeding. It probably is moving agriculture around, so some areas will not be favorable for the crops that are growing, so they'll have to move other places. We are seeing, so there has been this debate and discussion in the whole area for some 20 or 30 years about autonomous adaptation. Well, a lot of this just happened because you don't have to think about it that much. And in fact, there was a great map that occurred in the USA Today a year or two ago showing where corn was grown in 1980 and where it was grown today, and a whole bunch in North Dakota, which when we were in the Department of Agriculture, when I was there back in the 80s, we couldn't imagine North Dakota being a corn producer. It was just too cold. The season was too short. But now you are actually seeing a lot grown there. So that's the area there. In the human health area, from just the direct effects of heat, we've seen cities developing these cooling centers over the years, worrying about air conditioner or worrying about public health alerts. There is this whole vector-borne disease aspect of the problem, which is a huge concern. That's been kind of another murky area in that people have said, well, this much more area is going to become malarial. And then you'll have other people point out, well, Toronto was malarial before we had public health. So the public health component of that, spraying for mosquitoes or making sure there's not standing water around, is a sort of adaptation. In the water area, I think that's one of the big challenges, and that's one of the big investment challenges. Are our dams adequate? Will there be water to fill the ones that we have? And particularly when you look at this issue of snowmelt, the snowpack is a massive reservoir of water. If we don't have snowpack because it falls as rain, well, maybe we have to create man-made reservoirs, but that's an awful lot of reservoirs to hold. So we see California dealing with their drought at the moment, and I guess just incredibly record low snowpack, 6% of the normal or something, I think, just the news the other day. So what we do with water, where we get it from, do we transfer from another basin? Do we shut down activities, water using activities in a region? Do they get priced out of the market? What happens? So the adaptation thing runs, the gamut of almost every sort of investment we make. Do you need to kind of have more stronger roofs on areas in hurricane-prone areas because the storms have become more intense? So it really funnels down through lots of different things.
We got a question here.
So following up on the idea of water scarcity, do your projections take into account any potential innovations in desalination technologies, and do you see that playing part of the solution?
Yeah, so the water, that's a good question because it helps me clarify a point. Those water stress numbers are just if demand develops as it is and we don't then do anything to deal with it. So we're seeing those as kind of, we're seeing these projections as here's a world that might hit you, you better think of something to do about it. And so desalination could be an answer. More water storage could be an answer. Agriculture moving out of that area to someplace else could be another answer.
How about we take a question over there?
So we've talked a couple times about the different factors that affect, impacts. So we talk about, temperature increase in precipitation, decrease in precipitation, increase in amount of CO2 in the atmosphere. And all these things come down and have different impacts on the different sectors we've talked about. Water resources, agriculture, industry, energy production. A lot of the times, we can pick out the effects of a temperature increase on agriculture. But do you ever think about the feedback effects that the temperature increase would have on your water resources, and then thinking about how those water resources would change, and then bringing that back into how that would change your agriculture sector?
Yes, we've been working on this model, that part of the model, for about 6 years, and we finally have some of it together where we can then say, because of the water resource scarcity, there's less water available for irrigation in some of these areas. And so even though you might have had a increase in yield there, assuming there was enough water, now you don't. So that is, we haven't gotten that all together for the globe yet, but we have a version of the model for the US to begin looking at that. But that's the sort of integration challenge that I think is this cross-sectoral thing that kind of can maybe worsen the problem. And unfortunately, this integrated assessment modeling activity that's kind of it's built on. It says, gee whiz, if you just look at one sector by itself, you're going to assume I'm going to have some land and some water, but if the other sector is planning on having that too, there's only so much to go around. So resolving that is a important point of this integrated modeling approach.
Let's take a question from here.
I'm Linus Stevens. I'm a Humphrey Fellow in Boston University. Thank you so much for the lecture. I appreciate it. A little technical for me because I'm not an atmosphere scientist. But I have a mandate as my project to do an education about the climate change in schools in the Boston area in an artistic way because I'm a musician. So I see this issue of climate change not really as a subject of the academics, but subjects of humanity. If I go to high school to young folks, 13 to 15, what do I say to them about what is climate change? What are the factors of the climate change? What are the impacts of the climate change? And what do I say to them about the resilience? In simple language, without having to talk about hydrocarbon, without having to talk about polymers or anything. Thank you.
Clearly we scientists have failed and don't communicate very well because obviously the world is not listening very well, so we need you to help us out. I was at in fact, the Science Museum in Boston has been having some, have gotten groups of people together, I've participated in it, to kind of think about how they might develop an exhibit that would better educate people about climate change. And in that, they had a lot of, it was kind of interesting, they had people who studied the psychology of climate change or this communication. So there is a whole field in that. I don't know, the other sort of thing is, I know I had someone visited me, and they actually did a whole, I have a child's book that they wrote, and I have the author's signature on it, supposedly to kind of help educate people of climate change. So people have tried to do that. I don't know whether that book was successful or not, but I can share it with you at some point. I think you had sent me a note wanting to come over and talk, and I hadn't gotten back. But you should come over, and we can talk about it. You have to tell me what the answer is. We've obviously miserably failed in communication.
Hi, my name is Garrett Moore. I'm a senior here at Boston University. In a number of your models, you included mitigation strategies. What were some of the key mitigation strategies that were used in your models, as well as just in your experience of what are those key mitigation?
So in the simplest thing, we're putting on a carbon tax or a carbon cap and trade system, and so the price incentives are percolating through the economy and cause people to make other choices. We can also do things like renewable fuel standards or, or CAFE standards, and we compare and contrast those different things. I guess, coming from a big engineering university, I will say there's sometimes a bias that the solution to climate change is some engineering solution. And so we economists say, well, yes, but it's not, you can't just say the solution is nuclear without a strategy to actually get people to do it. And so we think the economic signals are the things that lead people to make different decisions. There is a whole technological, we model all these different technologies in our model, and so as a result of those economic signals, different of those technologies come in. More renewables, nuclear or carbon capture and storage, and just a lot of reduction in energy use we see because of the opportunities for improved efficiency. So it's a whole host of things. The other thing we have observed over and over again, we've done this for different sponsors, people will almost inevitably say, well, there's a lot of CO2 emissions, electricity is the biggest source, coal is the biggest problem in electricity, China and the US are the biggest coal producers. Let's do something about that. So let's shift the world from coal to gas, and that's going to have a big impact. And inevitably, when you narrow the problem down like that, you see very little impact on carbon emissions or climate, because when you start doing that, the problem leaks away, it leaks out. You don't use coal in the electricity sector, someone uses it somewhere else. You just don't get the bang for the buck. So that's the challenge of this problem. You need to hit it on all fronts. You start saying, well, my airplane is small, I don't have to worry about that. Everyone can say, my little thing is just a small piece. Can't I be exempted? But unfortunately, people of course are fascinated with renewable energy as the solution. That's a hard thing to make work. The costs of the basic costs are coming down, but unfortunately the wind doesn't blow when we need the electricity, and the sun doesn't always shine when we need the electricity. So the whole storage or backup or other thing is a massive exercise, massive problem. We've done some of the work with our climatologists that show that if you look at 20 or 30 years of climate data, there are periods when there's no wind anywhere in the whole eastern United States. And guess what? It happens in August because that's stagnant air, and that's when electricity is at peak. So you really need to kind of get down at that level to kind of think about what mitigation options work.
Could I I ask for you to go back to one of your very first slides, the one that shows the growth of energy consumption? I don't know how easily you can do that. That'll work fine. Is that, and it kind of feeds off the previous question. Can you see scenarios through policy decisions that will do two things? There's actually a missing slide here. One will flatten that energy use, right? But at the same time, there's another plot there, which is the GDP or per capita income on a PPP basis that won't cause that to dive. Because your model must predict that as well,
Yep.
right?
Yeah.
And so that's embedded here, and that the standard of living, both, especially in the right hand, the other G20 and the rest of the world, the issue is that a strategy that mitigates, right, the use of fossil fuels, but doesn't have an adverse effect on economies.
Yeah. Well, so the good thing is, while energy is really important to the economy, it is a sector that's only a few % of most economies. So as a result, we can spend 2 or 3 times as much on energy, and it's not going to sink the economy. So that's the sort of results we tend to get. So we would if we were trying to achieve a low stabilization level, we would have to put a fairly hefty carbon tax on, rising to about $1,000 a ton by the end of the century. That would dramatically reduce energy use, but that we would see as happening largely because of using energy more efficiently rather than doing completely without it. It does change the trajectory of vehicle purchases in China quite a lot, and some of those developing countries, they slow their use of vehicles. The economy continues to grow, and we get quite high economic costs because of the complexity of our modeling system. The IPCC came out recently, and they have a chart showing the range of models. Our model is not on there because they cut out the highest ones and the lowest ones. But even with that, we're saying it's a 20 or 30% hit to an economy by the end of the century, which sounds like a lot. But if you're growing at 5% a year or 3% a year, instead of growing 12 times, you grow 10 times. So economies are still growing dramatically, but there is some cost to it.
Hi. Sorry. Thank you so much for coming today. I was wondering, mitigation and adaptation policies are usually 2 separate things and are treated separately. And I was wondering if in any of your work you looked at combining the two, because there are some, especially mitigation strategies that are also adaptive. And I was wondering if you've seen any particular ones that work especially well.
Well, the area that's really interesting in that is the biofuels area, and we're doing a whole bunch of work on biofuels. So there the question is, might biofuels help mitigate? I guess there the question is that we're still going to have to adapt to climate change, and one of the impact where we have to adapt is agriculture. So how do those two interact? Is it good or is it bad? The findings we had there, which you saw earlier, was maybe we have a kind of a land policy which is sequestering carbon. That's going to affect your ability to adapt in agriculture because now you're taking away some of the land that otherwise might have been there for food. The synergistic mitigation and adaptation, we have some work we've done on water in the United States where the mitigation policy was dramatically moving us away from thermoelectric power plants. And so as a result, even if you were suffering more water, you were getting reduced water, you were reducing water stress because all of a sudden these thermoelectric power plants weren't around. We were using wind and solar instead. So that's an area where you might see some, positive synergies.
Going along with President Brown's question, and you also mentioned that the costs can still be, they can still be substantial growth despite the costs. would that still hold true for countries like Bangladesh or a lot of island nations where the impact of climate change is huge? I know in Bangladesh, almost half the country is supposed to sink by 2030. Other island nations like Fiji as well, sea level rise is huge. I've spoken to some ministers in these countries, and they've said the impact is so huge, the scale is so huge, that they're not even focused on integrating this into their economic growth policies. So just wanted to hear your thoughts on that.
Yeah. Well, Professor Brown's comment was, could I imagine mitigation and still having economic growth? So that's talking about the impacts and still having economic growth. So I think the small island nations, I mean, the reality is some of them will cease to exist because the sea level is going to rise so much that it's going to completely inundate them. So I guess the question is, what becomes of the country then? If it moves and we resettle it somewhere, God can only imagine what a disaster that would be, right? That country could continue to exist somewhere else, but those places are just, those very low-lying island states are most likely going to be gone. I mean, that's behind they've in the international negotiations, they were pushing for no more than 2 degree warming by 2050. No more than 2 degree warming. Now they've been pushing more recently for 1.6 because they think the risks even at 2 degrees of inundation is substantial. The challenge from the mitigation side I can imagine mitigating and not having a big impact on the economy. It's hard to see the world coming together as fast as it would have to do to get the 2 degrees, much less the 1.6. So, we were talking to some diplomats who are in negotiating teams about why if the 2 degree goal seems impossible at the moment, they still hold to it. And the answer was, well, we can't admit to a target that would, make some of the member states disappear. It's just not, it doesn't fit in the negotiations, but unfortunately, that's probably the reality of the situation.
Thanks again for your talk. It was very, very helpful, very informative. And I'm Ed Leckler. I'm a professor here at Boston University. When I see data like 40% of farming is due to irrigation, and then projected unmet demand on water, as well as drop in labor productivity, in the need for a 70% increase in food production, I begin to think that there might be a crisis point where you can't raise enough food, and at some point you hit some kind of a ceiling that leads to a crisis. In the same way on the water side as well, people don't have enough water, there's some kind of crisis that happens, and you get a kind of catastrophic event or series of events or the like. And I wonder if you ever look at your data and say, as I project that, it looks to me as if that is untenable, and that if that happens, something more than just a kind of another continuum is going to occur. There's actually going to be something dramatic that happens. And I apologize for asking the question. It's kind of a odd question, and it is a probably unknowable question. But for somebody who looks at these data a lot, I can imagine that every once in a while you see something and you say, that's just not going to work.
Well, it's a really hard challenge to put all these elements together, as I said. I mean, I've been working on this for my whole career since 1980, and we're finally getting some of the model structure together to actually ask some of these integrated questions. And then, the whole, what's the adaptation potential and how it's going to happen? and is it going to happen is a challenge. And I think that's been my biggest insight in the last decade or so, is that last slide I showed you about the humongous amount of variability. And so then that just asked me the question of, how do we adapt to that? I mean, we're starting some work in Africa, and we've been talking to development experts in Africa, and they were saying, and through some of our colleagues, they worked with the World Bank to show some of these distributions of uncertainty, and we were talking about, could we help them think about uncertainty and what it might mean for decisions? And they said, well, we saw that uncertainty from the World Bank, and it just caused people to not want to do anything. So I think this is the challenge of, I think one of the reasons people run away from this issue is it's so immense and it seems so problematic that maybe I just won't think about it at all and pretend it's not happening and do the best I can. I mean, you know, there's a little different version of your question than what you asked, but, you know, we're often, you know, some people are often saying, well, maybe there's going to be some catastrophe, and that will finally get people to kind of do something about mitigating this. And so, you know, so we're hoping that catastrophe shows up to cause it to happen. The challenge, the problem is that, you know, we saw Superstorm Sandy hit New York, and everyone got all excited about it, at least folks on the East Coast. But, you know, did it really change the mind of people in Texas and Oklahoma about climate change? No, not really. You know, we had, and now you can almost see that some of the urgency is going away, right? So these disasters break out in one region, they get all excited and there seems to be some things, but the rest of the country says, no, never mind, that's not the biggest problem, it's not affecting us. And so we have these disasters breaking out in different places, but you can't get the whole, you know, it's not happening everywhere in the world at the whole time. And so by the time people can get their act together and start thinking about it, they've forgotten about their disaster, or someone else hasn't had one, and we forget faster than we're able to move. So it's kind of a depressing story from that standpoint. You know, I mean, you know, the Defense Department is worried, and there have been some people that have called me up and asked me about these sorts of what is your kind of nightmare in terms of what might happen, seeing are there security threats that might come about. And I think the Defense Department is thinking about those, so I think there are people thinking about those. It's very hard. I mean, I was talking to someone who was in the Council of Economic Advisors about whether one would do something where these things unraveled and then you did an economic forecast. And he was remarking that he was there, he was in the White House in the, when we turned to 2000. Of course, then the problem of the year was what happens when all these clocks that can't deal with the year 2000 fall apart? Is the whole economy going to fall apart? So they said they did some economic projections. Well, what if all these sectors fall apart and the whole world collapses? Well, guess what? The whole world collapses because that's what you modeled. But it's hard to kind of, you know, say, well, is that really going to happen, or what's going to really happen, or how, you know, is this dire forecast compelling to people? So that's, I think the challenge is to kind of have it based scientifically enough so that it's compelling. Otherwise, it's creating a kind of a novel of doom story, which, you know, maybe is true, but isn't compelling to people.
We've got time for 2 more questions.
Thank you for coming. My name is Elizabeth Heenan. I'm a student at the School of Public Health. And following the question, so it seems like the problem is so big. Where do we put our money? What if we focus on taking our money out of what we know does not work? What is your opinion on divestment from fossil fuels?
You know, I know this is an issue here, and it's also an issue being discussed at MIT. I've wrestled back and forth. I mean, you know, there are of course people that say that divestment from fossil fuels is going to ruin the return on investments, and so people have kind of gone back far enough and said, I think there's a study out of the University of Chicago that says, oh, it's going to cause, if you took a portfolio from 1950 to present, with and without fossil fuels, one without fossil fuels does 23% worse. Other people have looked at the last decade and said, oh, look, you take a portfolio without fossil fuels, and it does much better. Obviously, going forward in the future, if we really believe we're going to have climate policy that's going to kind of take the steam out of fossil fuels, not being in them is a clever investment strategy, quite apart from what the signal might be. So I don't know really from that standpoint whether it's good or bad. I mean, the challenge here is what is it saying? It's really, I guess, it's a statement and a signal. It's really a political statement rather than having any real impact, because there are plenty of people out there who are happy to buy those stocks. So if you just take a little puddle of money out of it, someone else will take it, will buy them. So I don't really see it having any significant effect on the stocks themselves. So you really have to evaluate it. Is this a major political statement that somehow is going to get people's attention rather than any real effect of the measure itself?
Hi, you talked about some regions seeing increased precipitation. Do we have any sort of idea of what percentage of that increase is going to be useful precipitation and what percentage of it is going to be like Superstorm Sandy precipitation?
Well, so that's part of the challenge of these climate models. As big and computer intensive as they are, the ability to project precipitation very well is really poor. Now, from a basic science standpoint, you can logic that, the sorts of long, gentle rains result from advective processes, which are in cooler weather. The rain we see in the hot summer is convective thunderstorms, and that pops up in one place and deluges here and does nothing over there. So we think that's going to increase under climate change. So there is then more useless precipitation, if you will. Of course, that depends on, what the land cover is that we have. If we have, vegetation, then it can maybe collect even that deluging precipitation. If the land is bare or we have pavement, then that's just going to run in and cause flooding. It depends on what sort of storage facilities we have. If, again, we're going to get more of this heavy precipitation that runs off very quickly, then it may be that we need more, that means we need more storage. So you can probably use it in some way, but it may mean you have to think about it. I think, again, there's a question of, there tends to be more precipitation in more northerly latitudes or more polar latitudes, towards the poles on either side of the globe, and less precipitation in subtropical areas. So that's kind of the broad pattern that we think is going to happen. But again, the challenge with water is that, I think, as in so much of the world, is that, and this is really the science challenge, I think we know a lot about how the world works, but a lot of what we know about how the world works is we take as a base that things are going to continue to be the same they are, right? Once you start changing all of that, then all our smart, clever things that we thought worked suddenly start going haywire because the system is different than what we expect. So that's a little bit about the agricultural challenge as well. We grow crops in places that we've grown them for a long time and experience has said they've done well. All of a sudden, if it changes, I don't think our predictive models I know our predictive models don't do very well of just picking that crop model up and putting it somewhere in a different place and letting it grow. So I think the challenge, I've twisted your question around a little bit, but it becomes what is really useful, and we can make anything useful, but we can make these different resources, water resources, useful, but we have to have the whole system ready to know how to do that.
Thank you, Dr. Reilly.
Thank everyone for coming. I think there's going to be reception outside, so, and Dr. Reilly will be here if you have any other questions or comments. Thank you for coming. Well done.
Thanks.